Hi, I'm Changmin. I'm presenting prediction and generalization over directed actions by grid cells. This is a joint work by myself, Timothy Behrens, and Neil Burgess. Generalization should be possible in situations where actions have similar effects across states and across environments. Knowing how the effects of these possibly directed actions is the key to such generalizations. It is proposed that a cognitive map exists that encodes the relationships between objects in the state space and supports flexible planning and generalization. The hippocampal play cells and the entorhinal cortical grid cells are thought to instantiate such a cognitive map, which we show the spatial firing profiles below. Barham et al. In 2018 proposed the intuitive planning, a spectral model for efficient prediction and planning. Specifically, they represent the state occupancy distribution as a weighted sum of the eigenvectors of the transition matrix. So the predictions of the future state occupancy distribution by applying the transition matrix is transformed into the element-wise scalar multiplication by the corresponding eigenvalues. Furthermore, we can generalize the prediction to arbitrary number of time steps into the future, hence constructing the successor representation, which can then be used for guiding planning. It has been further shown that the eigenvectors of the SR encoding place cells firing profiles resemble the grid cell firing, hence relating the neural grid codes to prediction and planning. But note that the intuitive planning in its original form cannot support predictions of the effects of multiple directed actions under the same environment. Moreover, each separate task structure will require separate eigendecompositions, hence limiting the scalability of the method. We intend to address these issues and propose a more general planning framework based on intuitive planning. Specifically, we're going to focus on the Succulent transition matrix, which means that the transition structures are translation invariant across each state. We know that all Succulent transition matrices of the same dimensions share the same eigenbasis, consisting of the Fourier modes, which are just plane waves in two-dimensional environments shown on the right. By Fourier analysis, we know that the corresponding eigenvalues are just the discrete Fourier transforms of the first row or column of the transition matrix. Under the same environment, given different actions, the eigenvalues can then be updated efficiently using the Fourier shift theorem. Hence, the Fourier basis acts as a universal basis supporting predictions across all valid actions under the same task structure, including predictions of the effects for both the plane translation and translation plus diffusion as shown in the figure below. We can then define the set direction quantity as a linear combination of actions that maximize the probability of reaching the target state given the initial state in the following form. The sense of direction supports overall navigational strategy regardless of local details that deviate the transition structure from translation invariance. The resulting model utilizing the sense of direction style navigation supports flexible planning and arbitrary directed actions, as well as in environments that break the translation invariance or the periodic boundary conditions. Based on the proposed model of including explicit Fourier inputs into the computation of a metric for guiding spatial navigation, we included the Fourier modes of the state space as inputs and an additional subnetwork with action and state-dependent weights to a DQN to allow it to learn efficient prediction of future states and thus of the corresponding rewards. The proposed neural architecture is termed as grid cell DQN or just GCDQN. We demonstrate the utility of GCDQN through experiments on non-spatial reinforced learning tasks such as the carpool. We show that our GCDQN significantly outperforms the standard DQNs. We show that our prediction model is equivalent to models of grid cells based on path integration, because path integration is equivalent to predicting the effects of actions on state occupancy distribution in the spatial domain. For the continuous attractor network models, we follow the analysis by Sorcia et al. Based on pattern formation theory, and show that under directed actions, the dynamics equations governing the CNN updates are equivalent to the derivatives of the Lagrangian equation underlying the optimization problems entailed by the prediction models. For the oscillatory interference models, we show that our model generates the grid cell firing patterns in a qualitatively similar way as the oscillatory interference models. Moreover, the theta phase of firing corresponds directly to the complex phases of eigenvectors multiplied by eigenvalues, hence showing that our model correctly captures the theta phase precession in the synthesized grid cells that are observed experimentally, also in a similar way as the OI models do. In summary, we have shown that by choosing to represent state occupancy
using a single basis set that function as eigenvectors for all translation-invariant directed actions. The network can efficiently predict the effects of these actions and generalize to predict their effects in new tasks in both spatial and non-spatial domains. Based on the proposed model, we provide a unifying analysis of the past integration and prediction models of the grid cells firing. The ID of our paper is 1555 and the link is attached. We are at poster session 4, so if you're interested, please come and talk to us. I want to thank my co-authors, Neil Burgess and Behrens, as well as the listed people for helpful discussions and comments. Thank you for your attention.